So now you've had some experience carrying out a simple regression. Now let's look at a more general case, which isn't actually that much more complicated. So your learning objective for this video, by the end of this video, you should be able to define your basis functions, set up your G matrix, and then carry out, well, that will allow you to set up a general linear least squares regression. So you're going to define your basis functions. You should know how to do that. And the G matrix for doing a general linear least square regression. So when you did your, so previously, you fit a line to your data. And that line had the form of something like M1, coefficient 1, which is the intercept, M2, which is the model coefficient 2, which is the slope of your line, is equal, you tried to find that best fitting line that fits your data. And you did this, you set up the following matrix equation. Or I should say linear algebraic equation, where you put your, so M1 was multiplied by 1s, and M2 was multiplied by the different values of x's, and this was a deviation from the reference value of x0, all the way down to, you had n data points. And again, so you multiplied that by your model coefficient vector, m, and you took the deviation from your other data measurement, d1, d2, all the way out to the nth value of d. X was your location of your measurement, d was your measurement, and this defined your error vector. And this gives your linear algebraic equation, big G, your G matrix, times your model vector, minus your data vector, and that gives your error. And so the problem was to solve for m such that you minimize the square error. And that's why it's called a least squares regression. So just to describe these in a slightly different form, we were using two basis functions. So the first basis function was a constant function. We'll call that f1 for now. f1 is generally a function of x, but in this case it wasn't a function of x, it was a constant, and that constant was 1. And the other function was a line function. And we could call that f2 for now. It's a function of x, and that in that case was x minus x0, where of course x were the different values of x in our data. And so we can describe G as as containing two columns, each with each function evaluated at every point of x. And they're basis functions because they make up the basis of the functions that we fit with our function coefficients. But we need not be limited to, a constant and a line. We can do a more sophisticated regression by using any number of other sets of basis functions. So, for example, we could call our first function, I'm going to use g for function instead of f, just another variable for denoting function. So our first function of x we could call, well, let's just say it's a constant, just like our original case. Our second case was a line, And let's look at a third basis function being x squared, and a fourth being x cubed. And with this, we can fit our data with a third order polynomial. That is model coefficient 1, which is just our constant, plus model coefficient 2 times x, plus model coefficient 3 times x squared, times model coefficient x4 times x3. And again, we're going to, I guess these are vectors, and we're going to subtract our data vector to get an error function, and we're going to square that and minimize that. Alternatively, we could use periodic functions. Where g1 is equal to cosine of x, g2 is equal to cosine 2x, g3 is equal to cosine 3x, and so on. We could use m functions and make the mth function cosine mx. And when we do that, of course, we're going to solve the system m1 times cosine x plus m2 cosine 2x plus m3 cosine 3x all the way up to the mth coefficient for cosine mx, and we're going to subtract our data vector, again these are all vectors, and get our error vector. And this is what we would use in spectral or Fourier analysis. So we would find the coefficients for each of these periodic functions that minimize the deviation from our data. So in general, we can set up any number of basis functions, and these basis functions go into our G matrix. Oops, and I'm noticing I was a little careless here. G3 is equal to cosine 3x, and gm is equal to cosine mx. Right, so the first column of G, for example, would be our first basis function. And the first row would be the first value of x. The second column would be the first column is still our first basis function. The second row is our second value of x, all the way down to the nth value of x. So this is our first column is our first basis function. Likewise, our second column is our second basis function. And then if we have m basis functions, we would go out to, that would be our mth column. As such. Okay, and we solve the same equation. G, or I should say we minimize the same linear algebraic equation. And so this regression is general because we can put in any number of basis functions, and it's linear because the model coefficients they're multiplied individually by the different basis functions. Or in other words, we see this is a linear algebraic equation because m is a linear term as a vector in the equation. Okay, so this is how we set up our system, and you can read about how you go about solving for m by, again, minimizing e squared.